Hi. Hi, Star. This is the 12th lecture in the series on metric spaces. And let us hope that this is the last lecture of the series for a while. Okay. All right. And we are going to characterize continuity of functions between metric spaces in terms of open sets, the so-called inverse images. What we will define that in a minute. Okay. And actually, I started the lecture 10 minutes ago without mic on. So I have to again start recording, but let's see. I will share the screen. You see, you can see I had already done something. Okay. So in the last lecture, what we did was if f is a continuous function from the metric space xd to yd, fix a point A, then we proved f is continuous at A according to epsilon delta definition, if and only for every open set V in f containing f of A in Y. I can find an open set U in A so that f of U is contained in V. This is if and only. We proved it. Okay. And what we observed was something very interesting. If f is a function from x to y, of course, metric spaces, and assume f is continuous on all of x, start with any open set V in Y. Then look at the set U, which is set of all x in x, so that fx belong to V. Then this set is a set of x and it is open in x. We observed that. Okay. There is a name for this set, but I don't want to interrupt the lecture. I will finish another portion and then I will start doing that. Okay. So what is the natural question you can ask now? See, what is the hypothesis? F is continuous. What is the conclusion? If E is an open set, look at the U defined like this, then U is open. Okay. For every open set V, this happens. So what is the natural question you should ask? Whether the converse is true. So what is the converse? So let F be a function from X to Y. Okay. And it has a following property. What is the property? Give me any open set V in Y, then define U like this, set of all X in X so that Fx belong to V. I know this set U is open. Then can I conclude F is continuous on X? Do you understand? So we are looking at the converse. You see that it's going to be utterly trivial. Let us prove that. Okay. Why? What is happening? Yeah. Things are not working today. Something or other keeps going wrong. Anyway, so converse f from x to y, a function such that for every v open in y, the set u, which is set of all x in capital X, such that fx belong to v. This is open in x. Okay. Conclusion: f is continuous on x. This is what we want to prove. Okay. When I say f is continuous on x, what is the real meaning? It is continuous at each and every point in x. So let a in x be fixed. I will prove f is continuous at a. So since a is arbitrary, that would mean f is continuous on x, right? Okay. So to prove f is continuous at a, okay, that's to prove this. Okay. What I have to do? Let's go back to the definition. What did our definition say? This equivalent condition said, you give me any open set containing fa in y, then there is an open set u containing a, so that f of u is contained in v. Let us see that. So using the characterization, okay, if you want to call it result 1, okay, theorem 1, okay, for today, this is some lemma 2, okay. I now did like that, right, in my lectures? Anyway, so by theorem 1, okay, we will use theorem 1 rather. We shall use theorem 1 to prove continuity of f. So let v in y be open, and such that f of a lies in v, right? Now v is open. Therefore, what is the set u? U is the set of all x in capital X, such that fx belong to v. So by hypothesis, what do I know about u? I know this is open. Where? In X. Now notice that f of A belongs to V, that means A belongs to U. Do you understand that? Therefore, U is an open set which contains A, and start with any X in U by very construction fx belong to B. You understand that? F of U is contained in V. Therefore, F is continuous at A. Therefore, F is continuous on A, on X. Okay, pause, review, proceed. So, PRP. Okay, isn't it easy? Right? As I said, it's extremely simple proof, right? The converse, very good. Now, what do I want to do? So, let me give a kind of a jargon which is needed, and many times students, okay, are not very comfortable with the notion. Okay, so I will take some time. Okay, some background in set theory. Okay, there is no metric space, nothing now. Let x, y, or y be sets now. Okay, not necessarily metric spaces. Let f be x to y, be any function, a map. Okay, so this is my x, this is my y, and this is my f. Okay, now what do I have? Suppose I am given a subset B of y. Okay, right? Then what did we do? I want to define a subset A of X. How did I define? Exactly the same way I define U. How did you define? Set of all X in X so that Fx belong to B. You understand this? Okay, this set has a notion. This is usually denoted by F inverse of B. Okay. Okay. Therefore, F inverse of B by definition is X in X such that Fx belong to B. This is called, we read it F inverse of B. The actual thing is, this is the inverse image of B under the map F. This will be the much better way of saying. Okay. There are few things you should be cautioned about. Okay. Because this is a very kind of gray area for many students I have seen. Okay. Notice that these notations are somewhat bad notation, because students immediately think, they think of this, it is the image of the set B under the map F inverse. If I want to define F inverse, what should I assume? F must be a bijection. But did we assume? No. You understand that? So this object is defined whether or not F is a bijection. For any F, I can define this. So therefore, this is just a bad notation. Think of it as a single unit. Don't think of it as the image of B under the function F inverse, because F inverse may not even be defined. Okay, this you should think of as a single unit. F inverse B. That's it. Given a B and F, this is a notation, right? So think of it as a notation. In some sense, it's a bad notation, but you have to live with it. Just a quick example so that you will have, suppose fx from R to R, f of x equal to x squared. This is my favorite example. All right. Now suppose I take my set, okay, or let us say B to be 4. Then what is f inverse of this B? This set of all x real number so that f of x equal to 4. That is same as saying x squared equal to 4. That is same as saying it may be plus or minus 2. Do you understand? Right. Now the next thing, suppose I take something like 0 to 4. This is my B. What is f inverse of B? This is again set of all x real numbers so that fx, that is equal to x squared, lies in the interval 0 to 4. Right? So you usually say 0 to 2 will be there. But notice that minus 2 to 0 will also be there. Therefore, this is equal to minus 2 to 2. Do you understand this? Yeah. Okay. Now suppose my B, the same thing, minus 5 to minus 3. What is f inverse of B? This set of all x in R, so that f of x equal to x squared should lie in the interval minus 5 to minus 3. So in particular, it should be negative. Is there any real number whose square is negative? No, therefore it's empty. Yeah. So as our last example, let us start with something like minus 9 to minus, okay, yeah, minus 9 to 4 or minus 9 to plus 9. This is my B. What is f inverse of B? Notice that f inverse of B is same as f inverse of the set 0 to 9. Yeah, because minus 9 to 0 union 0 to 9. But f inverse of this is empty as we saw just now. Do you understand that? And what is this? This we know. It is minus 3 to plus 3. If this is the first time you are coming across this, please pause, review, proceed. Okay, spend some time. Okay, many students are confused with this notion. What you should remember is this is just a notation. It's a bad notation, right? And what it means is it's the inverse image of B under F. So F need not be bijection. It could be any function. So there are two facts which I want to, two or three facts which I want to do. Okay, again we are in set theory. Suppose Bi, okay, is a collection, okay, of subsets in power set of Y, right? Then we had already defined what is meant by union Bi in our course. This is a subset of Y. Okay, therefore I can look at what is f inverse of B. Okay, we claim it is nothing other than the union of f inverse of Bi. You understand that f inverse of Bi are subsets of X. Therefore, this will be union of subsets. Okay, you understand this? Okay, proof is extremely simple. I'll go little fast. You should get used to that. So to say these two sets are equal, what should I do? This set is a subset of this set, and this set is a subset of this set. So let us start with one, f inverse of B. So now we'll go back to the definition. When some x belong to f inverse of B, now that is what you have to learn. The only way to work with the f inverse B is you have to ask question, very easy question. When does x belong to f inverse B? If and only if fx belong to B. So when does x does not belong to f inverse of B? If and only if fx is not in B. Yeah, keep that in mind. We will use it. Therefore, this if and only if fx is in B. Right? Right. But when does fx is in B? There exists I. What is B? B is a union of Bi's. Therefore, there is I in I, so that x belong to f, f B, Bi. Right? B is union of Bi. Therefore, there is an I, so that x belong to Bi. But this is if and only if, okay, there is I in I, so that x belong to f inverse of Bi. Right? You understand that? Yeah. And this is if and only if x belong to union f inverse of Bi. Do you follow that? Go slow. Let us start with x and B inverse B. That happens if only fx is in B. But what is B? B is a union of Bi. So when does an element belong to the union? There is at least one index so that x belong to the particular set. Therefore, there is an I so that x belong to Bi. Now let's go back to the definition. What does it mean to say x belong to? Sorry, fx belong to Bi. See, right? Fx belong to Bi. So when does fx belong to Bi? If okay, let's that by definition of f inverse Bi, yeah, there is I said that x belong to f inverse of Bi. The moment x belong to f inverse of Bi, then it belong to union, right? So we proved it. And converse is also true. If x belong to union f inverse of Bi, that means there is I said that x belong to f inverse of Bi. But that is same as saying there is an I said that fx belong to Bi. That is same as saying fx belong to B because B is the union of Bi. That is same as saying x belong to f inverse of Bi. Okay, please pause, review, proceed, because these things are never taught as a rule unless you are done through MTTS or foundation book. and teachers also are not aware that the students may not have learned it properly. Now, what is the next question you should ask? Same thing with intersection, right? So we want to prove F inverse intersection Bi. I want to know whether it is equal to intersection of F inverse Bi. See, should I write this? I hope you will not be angry if I don't write. Okay, intersection over I and I, etc. Right? Okay. You saw that I proved both ways. Right? X belong to this. If only X belong to this. Okay. Same way I will going to do that. Now let's start with the next here. So X belong to F inverse of intersection Bi. So I'm not writing I in I. Okay. If and only if Fx belong to intersection Bi. This if and only if for all I Fx belong to Bi. This is if and only if for all I X belong to F inverse of Bi. But this is if and only if X belong to intersection F inverse of Bi. Okay. I don't want to repeat the argument. Okay. You stop the video, pause it, review it. Okay. Then there is a last one. Okay. Now what do I do is start with the B. This is the third observation. The second observation is about intersection. First observation is about union. Okay. These are the three facts about the so-called inverse images. Okay. Right. Now you can start with y minus b. This is the b y complement, right? Then I can look at f inverse of b. That will be a subset of x. Therefore, I can look at its complement. Now this is a subset. Okay. Keep a picture. This is your y and this is your b. And your y complement is going to be this. B complement is going to be this. So I'm looking at this. Okay. Now here what is the picture I have? I have x and this is going to be my f inverse of b. And what I am looking at? I am looking at these objects. Okay. This is this and this is this. The coloring scheme is nice. I hope you understand. Yeah. Right. So I do not know whether there is any relation at present. So let me start with this x minus f inverse b. Start with an x here. What does this mean? This means, see, x belong to x and x does not belong to f inverse of b. Right? It's in the complement. Therefore, it's same as saying fx. But this is same as saying what? X belong to x and fx is not in b. Right? Okay. See, now you can see this is superfluous. I don't need this because fx is not in b. That means where does fx belong to? Fx belong to y inverse of b. Fx is not in b, right? So I start with an x here, okay, which is not in f inverse b. Then fx, what do I conclude? Fx is here. Right? Which is not in b. Yeah. But what does this mean? This means x is in f inverse of y minus b. Because y minus b is a subset of this. What is our definition? X belong to inverse image of this side is fx in this. Yeah. So what have we shown? We have shown that x minus f inverse b is same as f inverse of y minus b. Okay. Don't worry about x and y. If it confuses, take the complement of b, its inverse images, Take the complement of F inverse B. That's it. They are equal. So these two are equal. Okay. Very good. So now let's go to the definition. What we have done so far is the following. So I have said F is, now we are back to metric space. So F is a function from X to Y. These are all metric spaces, right? And we have seen F is continuous on X if and only if, okay. In terms of inverse images, what you have proved is F inverse of V is open in X for every open set V in Y. This is what we have proved. So this is the theorem we proved in terms of inverse images. Do you understand this? Because F inverse V is what I call U. U was what? Set of all X in capital X so that Fx is in V. So in our notation now, it is nothing other than F inverse V. You understand? So what we proved, if F is continuous, if and only if you give me V, U is open. So it's same as saying F inverse V is open. Yeah? Make sure you understand. So we are characterize continuous functions from X to Y in terms of open subsets. What is another kind of question you can ask now? How do you define closed set? Complement of an open set. You understand? So what I can ask? Yes. Say it. Okay. You don't have to be shy. Yes. If a function, we want to say F is continuous, if and only if inverse image of every closed set is also closed. You understand? This is a conjecture. We don't know if it's true. Okay. So our question is this. Can we say F from X to Y is continuous if and only if for every closed set K of Y, let me call L of Y, the inverse image F inverse of L, call it K, is closed in X? This is a question. We do not know. But I'm sure all of you know what should be the answer. Yes. Why? Why do you think? Let's not worry about the proof now. Why do you think it should be true? What results we have seen so far should help you to say this is very likely to be correct. See, this is the way you have to develop mathematics and intuition. Okay, just because don't go by line proof. Try to develop intuition. Why do you expect this to be true? When is L closed? If and only if complement of L is open. Now what do you know? If F is continuous, then F inverse of the complement of L must be open. Okay, but complement of F inverse of complement of L, we know what it is. That's what we just now did. Are you following? At least you have some intuition, right? Let's look at the picture. The color picture. Suppose this is B is a closed set, then I know the complement of B is open set. Therefore, the complement of that, because F is continuous, the complement of this is open set. If that is open, that means F inverse of B is a closed set. Because why? You take F of the inverse image of F inverse of B. I want to say it's closed, right? And if it's closed, only if the complement is open. Have I proved it? Yes, because complement of B, the inverse image is complement of F inverse B. Since F is open, this is open. Okay. Anyway, I'll go through the proof. Okay. Proof. Let us assume F is continuous. Let L be closed. Okay. This happens if and only if Y minus L is open. Okay. I'll just write L complement so that it will be easier. Right? Writing. Okay. Then what we know? Therefore, since F is continuous, then F inverse of L complement, this is open in X. But what is this? This is, we know X is F inverse of L. So this is open. This is by set theory. But set theoretic preliminary, argument, we know this set is nothing there. This is open. If the complement of F inverse L is open in X, that means if and only if F inverse L is closed in X. Yeah. So what did we assume? Let us start with F is continuous. Then what did you prove? Let L be a subset of closed subset of Y. Then that means the complement LC, that is Y minus L, is open in Y. Since F is continuous, F inverse complement is open in X. But by set theoretic argument, we know this is nothing other than the complement of F inverse of L. Therefore, complement of F inverse L is open is same as saying F inverse L is closed. Have you understood the proof? Okay. So we proved one way. The converse part is we have to prove. That's also equally easy. Why? So what is our assumption now? Assume F has a property. What is the property? For every closed set L in Y, F inverse L is closed in X. So we want to prove F is continuous on X. Right? Okay. To say F is continuous on X, okay, right? Let us do that. Yeah. So let us use our open criterion. So let B in UI be open. So I have to prove F inverse B is open in X, right? To prove continuous on X, this is enough because that's our theorem, right? We proved it today, right? Okay. Now since V is open, but what is the hypothesis? Hypothesis deals with the closed sets in Y, and then the inverse image of such closed sets is closed in X. So so how will I generate such an L here? Obvious, right? That is Y minus B. That is my L. That is B complement. That's my L. Since B is open, this is closed. Okay. Therefore, by hypothesis, F inverse L is closed. Right? But what is F inverse L? This is by set theory. By set theory, this implies F inverse L is same as, what is that? F inverse L, that is F inverse of Y minus B. This is same as X minus F inverse of B. You understand that? Complement of B is take the inverse image of B and take its complement. Okay. Try to internalize. Okay. Just don't be psyched by the symbol. Try to internalize. What does this deal with? Start with B, then take the B complement. Its inverse image will be a subset of X. That is nothing other than take B, take its inverse image F inverse B, and take its complement. Okay. Inverse image of B complement is the complement of inverse image of B. Okay. So that's the way to think of. Okay. Inverse image of complement is the complement of the inverse image. Okay. You can chant like mantra now. Yeah. Okay. Right. Okay. Now let's go back. So what do I know? I know F inverse L is closed. That means the complement of F inverse B is closed. That, what does this say? This says F inverse B is open. Have you understood the proof? Okay. I don't want to repeat the proof. You can always pause the video and review. That's the advantage, right? In the classroom, you have to ask me to repeat. Here, you don't have to ask me to repeat. You can ask me to shut up, just to pause and then review. Yeah, nice. Very good. So everything has an advantage, right? Okay, good. So let us show that. So what are the things we have shown? Okay. So we have proved various things. Okay. Continuity on a metric space, between metric spaces, if you want, characterized. In what way? One is using sequential definition. I want to say F is continuous at X. That means for every sequence Xn and X, Fx and converges to Fx. This should happen for every X, then F is continuous on X. The second thing is epsilon delta. That again, if F is continuous at X, for every given epsilon, there is a delta such that distance between x and x dash less than delta implies distance between fx and fx dash is less than epsilon, and that should happen for every epsilon. And third thing is, if you give me an open set in y, then f inverse b is open in x. And fourth thing is, if you give me a closed set in L, then f inverse L is closed set. Okay, so these are the four criteria. Okay, this is a big theorem we have proved. This is one of the important thing, because these are the things which will generalize to arbitrary topological spaces if you go to MSc. Okay, now there is a kind of an important dividend, a benefit of this. Do you remember when we were talking about open sets in R2 or R, etc.? I said, for example, let us look at the axis, x and y axis. Okay, the union of x and y axis. I said its complement is open. Then we looked at geometrically something. Okay, please go through it. See, okay. I said if I take a point, let us look at this distance and look at this distance. Take the minimum, then I can put an open ball. If I have this, then look at this distance. Okay, and this distance is very high from x. So look at this. Okay, so we took minimum of mod x and mod y. Then that open ball will be completely contained in R2 minus axis. Okay, so we didn't stop to rigorously check this. Okay, it could have been done in my book. It's done, but I didn't want to spend time on that. But I said later we'll give an easy way of doing all these things. Yeah, I'm going to indicate that. What is that? Okay, this is where, so this is a most important pearl of wisdom. Okay, to show a set in a metric space or in a topological space also is closed or open, use continuity. Okay, what does this mean? Okay, I will tell you. Let us look at the set U. The set U, for example, was xy in R2. So that what? The xy does not belong to axis. So when does it belong to x-axis? If y is 0. When does it belong to y-axis? X must be 0. Therefore, x is I 0 or y is 0. If one of them must be 0, which is same as saying, this condition is same as saying, this happens if only if x and y equal to 0. How many of you understand this? Pause, here we proceed. Therefore, this set S is nothing other than xy in R2, so that xy equal to 0. Right? Now comes the trick. Yeah? What is the trick? Let us look at. Let us look at the function f from R2 to R given by f of xy equal to x times y. This is a continuous function. Yeah? Why? We know R2 to R, xy going to x is continuous. R2 to R, xy going to y is continuous. Product of continuous functions is continuous. We proved in the last lecture. Right? This is continuous function. Right? Right. Now let's look at the singleton set 0 in R. Right? This is a subset of this. So this is your L. This is closed because every finite subset of a metric space is closed. Therefore, this is closed. Now, what is F inverse L? This is by definition set of all xy in R2 so that f of xy is 0. But what is this? This set of all xy in R2 so that x times y is 0. But this is our set. Yeah? Yeah, you understand that? This is the complement of our set. Okay? Yeah. So this is closed. Okay? This is the axis. Okay? Therefore, what do you think I proved? The axis is closed. Yeah? Because this is a closed set. By continuity characterization, F inverse L must be closed, but F inverse L is nothing other than axis. Therefore, axis must be a closed subset of R2. Conversely, rather equivalently, the complement of the access, namely the set which you wanted, is open. Do you follow that? I'll just give another observation. Take any kind of your conic section in the Euclidean plane. Usually it's given by a quadratic polynomial, right? Right. So any conic section is a closed subset. So how to why? Because it will be a quadratic polynomial. F of x y equal to something. Summation. You know how to write it. X squared plus bx y squared plus something, some blah 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 blah. I do not write all such things. Okay. And this is a continuous function. Therefore, how do you give a conic section? For example, let us say rectangular hyperbola set of all xy such that x times y equal to c. You understand? Therefore, it is, if I define f of x y equal to x times y, f inverse of c is a rectangular hyperbola. Right? This is a closed set. Singleton C is a closed subset of R. Therefore, rectangular hyperbola is closed. And so on. Okay. More generally, suppose I give something like that. Okay. Suppose I have x in Rn. Okay. X is x1, x2, xn. Right? Something like this. a1 x1 plus a2 x2 plus an xn equal to 0, where a1, a2, an, okay, are real numbers. Rn, not R to Rn. This is again closed. Okay. In the case of R3, notice that this will be something like ax plus by plus c is equal to 0. Assume a, b, c is not equal to 0. Then this is a plane. So what have you shown? A plane is a closed subset of R3 and so on. Okay. Please refer to my book. There are a lot of good examples. I almost forgot one important thing, which I promised when we were discussing open sets in Rn. If any of the matrix D1, D2, and D infinity. So we will just have a look at that, and just about 10 minutes maximum, we will do that. Okay. So let look at Rn. D to be any one of the matrix D1, D2, or D infinity. Right? And let's look at tau 1, tau 2, and tau infinity be the topology of open set. This is, for example, tau j. What is it? It is U in Rn. So that U is open in dj metric, where dj is one of these d1, d2, d infinity. So what we want to say is all are equal. Okay. This we promise we will prove it. Okay. The proof is very easy. The crucial point is, okay, let vk be a sequence in Rn and v be an element. Then we know when does vk converge to v. Let us write converge to v. Let us write vk as xk1, xkn, and v as x1 to xn. Then vk converges to v with respect to any metric d, any metric g, dj. Fix a metric dj if and only if, okay, xki goes to xi for all 1 less than or equal to I less than or equal to n. And what is the advantage of this? Vk converging v is in Rn with respect to the one of the metric d1, d2, or d infinity. Here, these are all real numbers. This is a sequence of real numbers. Therefore, convergence of a vector sequence, okay, we had said it is equivalent to convergence of n real sequences. For each I, we have a sequence. Okay, this we had already seen, so I don't want to repeat. Keep that in mind. This is all we need. So let us look at the metric space Rn with respect to, let us say, di, where di is again the same thing. Rn with respect to the metric dj. Where are di, dj? They are in d1, d2, d infinity, any one of them. Even di may be dj, I don't care. Okay. Now let's look at the identity map. Call it f so that, okay, f is the identity map. That is, what is it? F of x equal to x for every x in Rn. Sorry, every v in Rn, let us say. Every v in Rn. Right? Okay. I claim F is continuous. Notice that this is a metric space. Rn with di is a metric, and this is Rn with dj as a metric. So in some sense, they are different metric spaces, but the underlying set is the same, namely Rn and Rn. Therefore, the identity makes sense, even though the metrics are different. So we want to say Rn is F is continuous on Rn. So fix a point V in Rn. So I have to prove F is continuous at V in, let us say, Rn di with respect to di metric, right? So to prove that, let's go back to the sequence definition. What did it say? You give me a sequence Vk in the space, which space? Rn di, right? So that Vk converges to V, right? Where in the metric di. Then what is that I have to prove? I have to prove, look at the matrix F, the sequence F of Vk, I have to prove it converges to F of V. In which metric? In the space D, Rn with dj metric. But what is Vk? Vk, F of Vk is Vk. What is F of V? It is V. Therefore, I have to prove Vk converges to V in dj. But remember, we had already proved it. Why? Because Vk converges, keeping the above notation, Vk converges to V in di if and only if Vk converges to V, okay, in dj. Why? Because Vk converges to V simply means the coordinate is convergence. xi converges to xi for each I. This is a sequence of numbers. There is no metric, nothing, right? It's a metric of R. Okay, this we already know from earlier, right? So what have we shown that? So we have shown that if Vk converges to V in di, then Vk converges to V in dj. This is clear? And conversely, let's look at the map. Okay, so is that clear to you? Pause, review, proceed. Okay, so what does this say then? Now suppose V in Rn dj, that is V belong to tau j, is open here. Okay. Now since F is continuous, what do I know? F inverse of V is open. Where? In Rn in the domain di. That is same as saying it is an element of tau I. This is given because F is continuous. You understand? But what is F inverse of V? F inverse of V is set of all x V. Okay, let me say this V is already there. Let set of all U in Rn, so that F of U belong to V. That is same as saying U in Rn. See, this Rn is the domain Rn. Okay, this is the V is in the codomain. But what is F of U? That is same as U. U belong to V. That means, okay, F inverse of V is V itself. Do you understand that? Identity map inverse image is itself. Do you follow that? So what have we shown now? We have shown that V, if V is an element of tau j, that is V is open in the metric dj metric, then V is open in the di metric. So V open with respect to dj metric implies V open with respect to di metric. But interchange I and j, then you have that. Say the same map you consider now with Rn dj to Rn di. Now suppose U belong to tau I, then F inverse of U will be U, therefore it belong to tau j. So if U is open in di metric, it is open in dj metric. Therefore what have we shown now? We have shown that and a subset U of Rn is open in di metric if and only if it is open in dj metric. So that means what? Okay, the topology is tau 1, tau 2 and tau infinity, they are the same. Okay, that's all we wanted to say. Yeah, so you can see that on the same set we seem to have three different metrics and the way they behave seems to be different, but the crucial observation was a sequence Vk converges to V if only if the sequence of real numbers of ith component converges to ith component of the limiting vector, limit vector. That observation helped us to show the identity map is continuous from Rn with any metric to Rn with some other metric. That these metrics are of course D1, D2, D infinity. We are not talking about general thing. There may be many other metrics. It may not happen. You follow that? So we have proved that. So when you want to talk about open sets on Rn, it does not matter whether you want to deal with the D1 metric or D2 metric or D infinity metric. Okay, that is the gist of this. I hope all of you understood. Okay, we will stop. My idea of these lectures is to kind of initiate you into thinking properly, right? Okay, I don't want to replace my book or your teacher's lectures or other textbooks which you may be following. But my book has a lot of such examples. Okay, how to use continuity to prove something is open, something is closed, etc. Okay, I hope you enjoyed this lecture. Okay, please go through it. And this is the last lecture of the series. We will meet later. But remember, there are already other after continuity. There is a lecture on something like uniform continuity. There is a lecture about compactness. Okay, equivalent characterization of compactness. Okay, those things you can learn on your own. If time permits, I'll come back to that. Okay, I would like to teach about density and sorry. Okay, because that's another concept which people should learn. Okay, if time permits, I'll come back to that. But have a good day. I hope you all enjoyed. And please write your comments. That's what will keep me motivated to give further videos. If you really like these things, you should show you appreciate that. Okay. Thank you very much.